Hello friends, have you ever wondered if we could shortcut our way across the universe? Picture this, instead of trekking across vast cosmic distances, we take a swift detour through a wormhole. What's a wormhole, you ask? Well, in simple terms, it's a theoretical bridge or shortcut through the fabric of space-time itself. Now, isn't that a mind-bender? These cosmic shortcuts are a hot topic in the realm of science fiction, making regular appearances in our favorite movies, books, and TV shows. But remember, as mesmerizing as they may be, wormholes remain purely hypothetical. Despite their omnipresence in pop culture, we've yet to lay our eyes on a real, tangible wormhole. So, here's the big question. Are these space-time bridges just a figment of our collective imagination, crafted by science fiction writers and hopeful astrophysicists? Or is there a kernel of truth hidden within the fascinating concept of wormholes? So, are wormholes just a figment of our collective imagination, or is there more to them? Before we delve deeper into wormholes, we need to understand the fabric they're made of, space-time. Imagine space-time as the four-dimensional fabric of the universe. It's a vast, invisible plane stretching out in all directions. Now, let's add the concept of time as the fourth dimension, creating a continuum. This space-time continuum is the stage on which all cosmic events play out. But what happens when something with mass comes into the picture? Picture a stretched rubber sheet. Now place a heavy ball at its center. The ball creates a dent, a depression. This is similar to what happens in our universe. A massive object like a star or a planet distorts the fabric of space-time around it, creating what we call gravity. This is an essential part of understanding how our universe works. So, what's the connection between this and wormholes? Well, wormholes are theoretical passages through space-time. They're like shortcuts, allowing you to hop from one point in space-time to another without having to traverse the entire distance. Sounds like science fiction, right? But remember, this is all rooted in the established principles of physics. Wormholes exist within the fabric of space-time. They are possible because space-time isn't a rigid structure. It's flexible and can be warped and twisted. This is where our analogy of the rubber sheet comes in handy again. If you could fold that sheet, bringing two distant points close together and then punch a hole through both layers, you'd have a rudimentary model of a wormhole. Remember though, this is a simplified explanation. The actual physics involved is much more complex and mind-bending. The theories and mathematics that describe wormholes come from the realm of Einstein's general relativity, a theory that has stood the test of time and continues to shape our understanding of the cosmos. Now that we have a basic understanding of space-time, let's venture into the realm of wormholes. Imagine a tunnel with two ends, each in separate points in space-time. Picture yourself standing at the entrance to a tunnel. This is not your ordinary tunnel, but a wormhole, an extraordinary structure that defies our understanding of space and time. Now, this tunnel, or wormhole, has two ends, just like any other tunnel you might think of. In the language of cosmology, these ends are referred to as mouths. One mouth of this wormhole is here with us, while the other could be anywhere, a distant part of our universe, or perhaps even in a separate universe entirely. These mouths are not just doors to different locales, but to different points in time as well. Imagine stepping into your local subway station and emerging on the other side of the galaxy, or even, in theory, a different era. Connecting these two mouths is a conduit known as the throat. The throat of a wormhole is not a straight line, but rather a shortcut, a bypass through the fabric of space and time. It's like folding a piece of paper in half and poking a hole through it. The 2 points that were once far apart are now connected by a direct path. This is the basic structure of a wormhole. This tunnel-like entity, with its 2 mouths and a throat, forms a bridge across space and time. It's a concept that seems to belong to the realm of science fiction, but is deeply rooted in the equations of Einstein's general relativity. However, it's crucial to remember that wormholes are purely hypothetical at this point. While the mathematics of general relativity allows for their existence, we've yet to observe one in our universe. They are elusive, fascinating, and hold the potential to revolutionize our understanding of the cosmos. Sounds exciting, doesn't it? But how could such a thing exist? Let's delve deeper and explore the science behind these mysterious structures in the next segment. The idea of wormholes comes from Einstein's theory of general relativity. You see, when Einstein proposed his groundbreaking theory back in the early 20th century, it revolutionized our understanding of space and time. He suggested that these two concepts are intertwined in what we now call the space-time continuum. Now, let's delve a bit deeper into this science. Wormholes are essentially solutions to the equations of general relativity. In simpler terms, if you have these complex equations of the universe, wormholes are one of the possible answers that can emerge. They are theoretical passages through space-time that could potentially create shortcuts for long journeys across the universe. However, even though the mathematics of general relativity allows for the existence of wormholes, we don't have any empirical evidence to support it. That's right, as of now, no one has ever observed a wormhole, and they remain purely theoretical constructs. But why is this so? Well, observing or creating wormholes presents a massive challenge. For starters, wormholes, if they exist, are likely to be incredibly unstable. They might open and close so quickly that nothing could pass through them. To hold a wormhole open would require something known as exotic matter, a type of matter that has negative energy density. Now, this exotic matter is also purely theoretical, and we've yet to discover anything in our universe that fits this description. Another challenge is that even if we could somehow stabilize a wormhole, it would be infinitesimally small, according to current theories. As a result, enlarging it to a size that would be useful for space travel, another popular topic when discussing wormholes, presents further complications. So, while the science is fascinating, wormholes remain a theoretical concept. We continue to study and explore these concepts, hoping that one day we might uncover empirical evidence that brings us one step closer to understanding the mysteries of our universe. Until then, the idea of wormholes serves as a testament to the power of human imagination and our relentless pursuit of knowledge. If wormholes do exist, they could revolutionize space travel. Imagine for a moment that you're not bound by the conventional limitations of time and space. Instead, you're able to traverse the cosmos in the blink of an eye, through tunnels in the fabric of reality itself. That's the promise of wormholes. In theory, wormholes could provide shortcuts across vast cosmic distances. They're like secret passages in the universe, linking two distant points in space-time. It's like folding a piece of paper in half and poking a hole through both ends. The distance between the 2 points becomes virtually negligible, no matter how far apart they might be on the unfolded sheet. Imagine what this could mean for space exploration. We could reach distant galaxies, explore far-off planets, and unravel the mysteries of the universe in ways we've never even dreamed of. The universe would become our backyard, ready to be explored and understood. However, it's not all smooth sailing. There are challenges and dangers that come with the concept of wormholes. For one, wormholes are inherently unstable. They require a type of matter with negative energy density to keep them open, something that remains purely theoretical at this point. And then there's the potential for time paradoxes. If wormholes can connect not just different places but different times, they could theoretically allow for time travel. But this opens up a whole can of paradoxical worms. What happens if you change something in the past? Does it affect the future? These are questions that still puzzle even the brightest minds. In conclusion, wormholes are a tantalizing prospect. They could open up new avenues for space travel and exploration, allowing us to reach corners of the universe that are currently beyond our grasp. But they also present significant challenges and dangers. While we're far from using wormholes for space travel, the idea continues to captivate our imagination. the concept of wormholes and their potential to revolutionize space travel remains one of the most fascinating topics in astrophysics, a testament to our enduring curiosity about the cosmos around us. Wormholes, a fascinating concept, a bridge across the universe, remain shrouded in mystery. Over the course of our journey, we've delved into the captivating world of wormholes, exploring the intricacies of their structure and the science that underpins them. We've ventured into the realm of space-time, peeling back the layers to understand the framework in which these cosmic shortcuts could exist. We've pondered the tantalizing implications for space travel, imagining a future where distances that currently seem insurmountable could be traversed in the blink of an eye. Yet, it's to remember that while wormholes are theoretically possible, they remain elusive. We've yet to observe or create one, and their existence continues to be the subject of intense debate among scientists. So, until we find a real wormhole, they will continue to be a source of wonder and speculation, a testament to the limitless possibilities of our universe. Goodbye, friends.